could you briefly say why you think it makes sense to have the have that discussion before the architecture discussion?
So we have it structured because of following a dependencies between them. So, but I think all of them are complements to each other. So.
Okay, thanks.
So it's expected that the protocol is self-contained, and in the architecture, you can get a broader idea of.
Okay, I think we can get started now. So this is Privacy Pass working group, our first meeting as a working group, which is pretty exciting. So here's some information which you probably already figured out if you're here. The one thing we do want to go through is the note well. So we'll leave this up here. It's the thing you've probably seen all week if you've been at a couple other meetings. Leave it up here for another couple seconds, and then I'll give it over to Ben if he has anything he wants to say. If not, then we can get started.
I'll just say thank you to our note takers. If anybody else wants to volunteer to help take notes, please dive into the CodiMD. It's a collaborative note taking, and we can get started. We have 3 presentations, and I will be managing the question queue. Please, as always, ask clarifying questions during the presentation, and we'll have time at the end of each segment for broader discussion.
Okay. So, okay, my name is Armando Faz. I'm working for Cloudflare, and this time I'm going to talk about the description of the Privacy Pass protocol. Next slide, please. So in this slide, we can see the relations between the proposed documents, and as you can see, I'm going to explain the Privacy Pass protocol, which is related to the architecture and also to the HTTP API. So I hope this slide explains a little bit why we started with the protocol first. So next slide, please. So the content of the document describes basically what is the meaning of the Privacy Pass protocol, together with the security properties that are attached and that are required for this to work. Also describe the phases of the protocol and describe the API that we expected to be used by any implementation of this protocol. So also in section 7, it gives a specific instantiation of the Privacy Pass protocol using BOPRFs. And using BOPRFs, we propose some cipher suites that matches with this BOPRF. And finally, there's a section for extensions that allows to the protocol that can be extended with another different implementations. So, well, let's start. Next slide, please. So first of all, some definitions. So it's important to note the difference between these two concepts. So authorization means like granting to privilege to users. Meanwhile, authentication is something that people just confuse, but authentication means like the process that is used to identify a user. So Privacy Pass protocol is about authorization. So in that sense, next slide, please. In that sense, the objective of Privacy Pass is to have an efficient way to generate tokens, which can be anonymously redeem it. So there are three main properties of this protocol: unlinkability, unforgeability, and the key commitment. So the first one, unlinkability. So any issuer of tokens, it must be hard for the issuer to link a redeemed token with other tokens that were previously issued. So this is a very strong property for keeping the privacy of the redemption. The second one is unforgeability. Of course, we don't want that tokens be generated off the air, so clients cannot redeem more tokens than those that were initially granted. We also required, or we must allow that the clients can verify whether a token that was generated by an issuer actually corresponds to a token that was generated using the secret key of the server. So with these are three main properties of this protocol, and we also want that the protocol be able to be extended with different implementations or cipher suites. So okay, next slide, please. So basically, the protocol is composed by three phases. The setup phase, which is an offline phase, which is very simple, is just the server generates a pair of keys and makes the public key available to the client, so the clients can fetch the server key before starting the protocol. So the two main phases of the protocol are the issuance of tokens, where the client interacts with the server in order to get tokens, and the redemption is when the client wants to redeem or to spend a token with the server as an authorization method. So okay, next one. So the issuance is a one round trip protocol. In this case, the goal of this is we want that a client can request a certain amount of tokens. In this case, the client starts the protocol by generating an issue request for the number of tokens that the client wants to obtain from the server. He sends the request to the server, and then the server, using the secret key, it prepares a response with tokens that are sent back to the client. So the client can process this issue request first for extracting the tokens, but also there's an important step here that he's able to verify whether the tokens were processed with the server secret keys. That's why he uses the public key of the server to have a guarantee that the tokens were honestly created. In the next one, so yeah, in redemption. In redemption, so now the client has in his possession a certain amount of tokens. So he takes one of those and he wants to spend this token with the server. So in order to do that, he started by constructing a redemption request with the token, which basically packs the token and sends to the server. The server, what it does is just parses this request from the client and verifies that the token is valid, and also verifies that the token hasn't been spent before. So this is in order to avoid double spending of tokens, which is important for this protocol. When the server has verified that this token is valid, hasn't been spent, so the server can create some request response to the client, which is basically one bit that says, okay, the client, you have the access granted, or you have the access denied, in case that something goes wrong. So the document describes with more details what are the types of this all of this API and what are the formats or data structures for the requests and responses. Well, this is in general like how the privacy protocol works. And now I will show you one instantiation of the protocol. So in the next one. So in this case, one of the instantiation of the protocol is using VOPRFs. So an OPRF is actually a protocol that can be used for collaboratively computing a pseudo-random function. So this pseudo-random function takes as an input the server key, secret key, and some client input X. And the output of that is equal to Y, which has this property that happens to be oblivious. That means that the client only can learn the output of the function, but there's no way that the client learns something about the secret key of the server. And at the same time, the server cannot. It's difficult for the client, for the server to learn what was the client input that he uses to compute the function. So with this property is an OPRF, and in order to get from an OPRF to a BOPRF, the V stands for verifiable, which means that the server has a way to prove to the client that the output of this protocol was actually computed with the secret key that that the server usually commits to this key. So this allows to the client to be able to verify that the output was corrected using that secret key. So in relation with this theoretical construction with the privacy pass protocol, so you may notice that the pair XY of input correspond to a redemption token. So what happens during redemption is that the server actually receives this token and internally checks whether this equation holds or not. So if it holds, so that say that the token is valid. Next one, please. Yeah. So the description of the BOPRF is in the draft. It currently provides some constructions which are based on prime order groups. And also the API of the BOPRF draft actually maps one-to-one to the privacy pass API. So as you can see, like the 5 functions that are used for privacy pass are mapped one-to-one to the BOPRF. So regarding the security analysis of this, so this instantiation holds with the 3 properties that I mentioned before: unlinkability, unforgeability, and verifiability. More details are on the BOPRF draft. Next one, please. Okay, so given that, so here we are proposing 3 different cipher suites for 3 different security levels, which actually map from the BOPRF suites that are defined in that draft. Notice that the list is expected to be extensible. So any other implementation or any other modification to the protocol is expected to have another cipher suite that can be added to this list. Also, you may note, and there's a small note that we are currently not recommended cipher suites at 128 bits of security, and this is because of the strongness of the static Diffie-Hellman problem. More details about, more technical details about this are on the BOPRF drafts. Next slide, please. Yeah. Finally, regarding the extension policy. So, as I mentioned before, we want that the privacy pass protocol can be extended either by different implementations or or different extensions of the protocol. So any new extension should add a new cipher suite to the list, and also must instantiate the API that we're describing. So it is expected that all of the new extensions have the same API. Of course, we want that the security properties must be satisfied in order to make any extension be compatible with the aims of the Privacy Pass protocol. So it is expected that these new extensions will be defined either in a document in the working group or as a part of this document core protocol. So there are some examples of what are some potential extensions to the Privacy Pass protocol. The first one is a PNB protocol or PNB tokens. Currently, the BOPRF doesn't allow to include certain metadata on the redemption tokens. But this extension, the PNB, it allows to include certain metadata bits on it. So the description of the protocol is on this EPRIN paper. Another potential extension to the protocol is to allow public verifiability. Currently, using the BOPRF instantiation, only the client can verify whether the tokens were issued with the secret key of the server. But with public verifiability, it allows that anyone can verify this property. So in the next one, please. So yeah, this is this is an example of how it looks like the public verifiable extension. So in this case, in order for this to work, it relies not on BOPRFs, but on blind signature schemes. So as you can see, the blind signature operations almost map to the Privacy Pass API. So the security of this protocol, is based on the properties of the blind signature scheme, and more details or more specific details are actually were already commented on the mailing list some weeks ago. So next one. Well, finally, this is the summary, so that this specific document only describes the Privacy Pass protocol, which is aligned with the goals of the working group. It provides a way to create unlinkable tokens using which can be used for anonymous redemption. It describes the API definition and also presents an efficient implementation using BOPRFs. With that, there are also defined certain cipher suites based on BOPRFs, and also allows to the protocol to be extensible. So this is briefly what the privacy protocol is, and then I will open for questions. Well, there are some questions on the chat, but there are some comments. Okay, well.
Ben, your audio.
Yeah, I can hear you.
You should have audio now. Yep.
Yes.
Now that's this is Joe. Ben, I don't think we have your audio yet.
How about now?
Yep, that's good.
Okay. So it says, please join the queue if you have comments. Ben Schwartz, chair hat off. I think that it would be helpful to avoid describing this as extensible, and instead just present it with the understanding that change control if adopted, would pass to the working group, and so the protocol might be altered. We don't need to think about this as a protocol with extensions. It's a protocol that we, if adopted, would then have the ability to modify.
Hi, this is Alex. So I think on the extensions front, what we're imagining is like the core protocol will have like a set of cipher suites, and any extension would just like append extra cipher suites to that. So it wouldn't, like, the extensions wouldn't interfere like with the actual like API or the message flow. It would just be about specifying like a new cipher suite identifier.
I want to try using terminology like agile or general instead of extensible. I think my main point here is that the working group has not made any statement that it's, for example, committing to using the VOPRF construction here. It's within the working group's power to say VOPRFs are out, PMB tokens only, in which case PMB tokens can't very well be described as an extension of the protocol.
Yeah, so that is something that can be added.
I guess one question, this might be more towards the chair, is like this extensibility question, like there's how the working group extends this protocol or changes the underlying protocol, and like what the like final work product of the working group is going to look like, and if it has extensibility after like we've, as the working group, have made all the decisions. And I guess I assume this extensibility more refers to the former, which is like part of the like passing over change control.
Yeah, so maybe we can draw a distinction between this slide that says extensible and previous slides that listed potential extensions. I think it's fine to talk about the protocol as designed to be extensible. I just don't think that we should necessarily speculate too much right now about what's going to be in the core protocol and what would be an extension. That's TBD.
Yeah.
Other comments? We'll move on to the next presentation. Okay, back to you, Joe.
All right, Alex, whenever you're ready.
Sure. Do we want to go with video? Or... Okay, cool. Yeah, so I'm Alex, and I'm going to be talking now about the architecture document that we currently have and how this relates to the PrivacyPass protocol that Armando spoke about. So next slide, please. So relating to the previous diagram that Armando showed, the architecture document focuses on how we integrate the PrivacyPass protocol into an ecosystem where there are multiple servers and clients. And then Stephen is going to relate like the HTTP API that we sort of talk about in the existing documents that we have after that. So next slide, please. So the protocol that Armando presented, we can think about as an atomic exchange between a client and a server, where there's like one channel, and the clients issue tokens by a server on that channel, and they redeem tokens with that server. And the protocol relates to like the cryptographic exchange and the API and how all of that is integrated. So next slide, please. And the ecosystem that we talk about in the architecture document builds out the context in which this protocol exists. So one of the core principles of the architecture document is to analyze the relationships between the clients and the servers. So the ecosystem of the like a privacy pass ecosystem contains like multiple clients and multiple servers, and a client engages in privacy pass interactions with those servers, and with multiple servers. So it's issued tokens by servers and it redeems tokens. And the reason that we talk about the ecosystem in these terms is because actually the privacy requirements of the protocol are only bear fruit in this context. So if we think back to the unlinkability requirement that Armando presented, the unlinkability requirement is only has utility in relation to the end tokens that are issued under a given key. So a client's anonymity is only within the set of all clients that are issued tokens under a given key. And so if that number of tokens is small, or that number of clients is small, or there's a significant number of keys, then the privacy of the client is actually diminished beyond the cryptographic guarantees of the protocol. So this is the system that we're trying to analyze in the architecture document and the entities that are involved. So next slide, please. So the organization of this document first takes into account the overview of the ecosystem and the different participants. So one of the things I didn't mention on the previous slide is the key management story, and that comes next. So actually, for this key committing property, we need clients to be able to retrieve the server's public key in order to check that issuance data is committed to properly. And so we have to factor into this ecosystem these like key registries, and that's something I'm going to talk about soon. And the key management story is actually also critical to the privacy analysis. And then from a functionality perspective, following that, we present a number of different modes in which servers and clients actually conduct interactions and recommendations for how those interactions should take place. And then based on those interactions, like we have the trust dynamics of the client and server. So clients and servers, well, clients should only interact with servers that they trust, and because like redeeming tokens for a given server reveals bits about the client's identity and its anonymity set. So that's something that we highlight, although it's more of a policy question that we don't really get into the specifics of, but I will talk about that later as well. And then the core sort of body of the document is the privacy and security considerations of the protocol, because the protocol only has utility when we can ensure the privacy of the clients, and then there are also security considerations associated with how the server runs. And related to those privacy considerations, we then give like concrete parameterizations of the anonymity sets that we could expect to construct given different settings and different like variables in the ecosystem. And then finally, we talk about how the extension policy that we mentioned in the protocol document like sort of also impacts the architecture. So next slide, please. So in this talk, I've synthesized like those sections into 5 key questions I'm going to cover, and each of these questions relates to a different facet of the document, but there are also open questions that are yet to be solved associated with each of these questions. So in this talk, I'm going to structure it around these 5 questions. So if we go to the next slide, please. So the first question is like, who are the valid token issuers and servers? So the privacy pass ecosystem is defined by essentially the servers that are issuing tokens in that ecosystem and which keys they control. So in the architecture, in the privacy pass architecture document, we kind of assume that a server is completely defined by the key that it is issuing tokens by with at any given time. So when we support servers, we essentially mean that we are making that key material available to the clients in the ecosystem. And if a server's key material isn't available to a client, then it's not supported in the ecosystem. So an early open question that we have around like how we embed these servers into the ecosystem is actually around like how we mitigate server centralization. So this is something that's come up in the previous IETF meeting and also on the mailing list, and it's like how we mitigate against like consolidation around a small number of servers that are admitted access based on some like policy which is like restricting the number of servers. So we need like a diversity of servers to ensure that clients are like being issued tokens by not just a small number of like centralized entities. And it would be good to get an idea of like some suggestions on how we should mitigate that, and also how we would structure that mitigation into like the documentation of this working group. The next slide, please. So related to like the server key identities, so a key functionality question is like, how do we actually make this key information available to clients? Like, how is it published? How do we audit that key information? So the recommendation that we make in the document currently is that server key information is stored in independent registries, which essentially like hold server key information at any given time, and servers can update key information by appending new keys to the list and invalidating old keys. And this key registry obviously has to be public so that clients can retrieve key information from them. And essentially here we have we're assuming that the registry in its independence is deciding which service to support, and clients transitively would also decide which key registries to support, and that's something we talk about in the future. But an open question around this is like, we give these recommendations around how a key registry should be built because I'm going to talk about it in the privacy analysis, but like there are concerns about how keys are updated and things like that, which affect the privacy of clients. But would it be interesting to the working group to specify such a registry concretely? And if we were to do that, would that exist here in the architecture document? Would it exist in like application-specific documents like the HTTP API, or its own separate document, or would we like take existing technology from elsewhere and like build out like key management story from using that instead? So next slide, please. So in terms of what these key registries actually look like, they contain essentially the data that's contained in any given configuration update is like the server identifier, which is like the fully qualified domain name of the server, the cipher suite the server is using at that time, and then the public key just the bytes of the public key associated with the protocol. So we require that only one valid key is permitted for any given server at any time, and so a server is completely defined by its key, and that key must be consistent across all the registries that the server participates in. So obviously this opens up like a big vector for auditing, and it's not clear as well how we like how that auditing is carried out, whether that's like client auditing or whether there's some like external entity that audits these key updates. But those properties are crucial in reducing the privacy impact on clients. And then so for key rotation from a functional perspective, like servers like send their key updates to the registries they're part of, and those key updates are appended to the list and the old data is invalidated. And likewise, if the server wants to rotate its cipher suite, then it must do so in a key update because there's only one valid key at any given time. So next slide, please. So on the third question relates to like client server trust. And so it's like, how do clients actually choose which service to trust? And again, so I mentioned before that we think this is more of a policy question, but essentially it's important that clients only store and redeem tokens with servers that they trust, because when they redeem a token, they reveal that they have interacted with that server in the past. But the important factors that we bring up in the document for ascertaining this trust essentially come down to whether the client trusts the key registry that's holding the server key data, and whether the like ephemeral reason for initiating this issuance redemption flow is something that the client trusts as well. So what we're imagining here is like maybe there's some list of key registries that the client trusts, and maybe it can edit that. And then the reasons for initiating the issuance and redemption are like controlled in the client implementation, and the issuance and redemption like interactions are only allowed in very like structured situations. So if we go to the next slide, please. So like a couple of things that we kind of think are likely to be like what we're kind of assuming would be the framework for this is like, in say like allow lists for key registries. So if we're thinking like the browser situation, like browsers would have allow lists for certain key registries in the PrivacyPass ecosystem, and they might be set by the browser, or like, and then clients could edit them afterwards. And then if we want to go slightly more granular, more granular level, then we might allow lists for individual servers. If like a server is identified to be trusted, like not trusted out of band, then we could add, then we could remove it from an allow list, say, or and likewise, we could also have block lists rather than allow lists. But these are kind of like open questions that we'd like to sort of get more opinions on as well. And a key open question that we have around this is actually like, how do we assess whether the server is acting maliciously in order to like ban it from the ecosystem or to like sanction it? So obviously, like there are mechanisms for checking whether the server is acting maliciously if they're posting strange key updates. Like for example, if they're rotating a key really often, then that will reduce the size of the anonymity set for any client that gets tokens from a particular epoch. But actually how we assess whether that is happening, and then how do we react to it? So if it's client administered auditing, do clients then gossip with each other to propagate whether they think a server is malicious or not, or do we have like regular external audits that are checking the key registries? So yeah, this is another open question. So next slide, please. So then the fourth question relates to like the server running mode. So these are actually like from a functionality perspective, what we recommend the interactions for client and servers to look like. So the client API, the two key principles that we want to try and enforce with these running modes is that the client API is equivalent in most of them, in the sense that the client doesn't actually have to change how it interacts. It's merely the entity on the other end that's kind of changing. And then the tokens that are issued to a client are completely independent of the mode. So when we talk about these running modes, we're talking about like the redemption side of the protocol. And so if an issuing server is exercising different running modes in different places, then the tokens themselves will be valid for any of those running modes. So if we go to the next slide. Firstly, on the issuance side, actually the flow of the protocol is pretty much a server authenticated operation. So I mean, the server could do something clever by like allowing trusted entities to issue tokens on its behalf, but essentially the client is performing some operation that the server trusts, and the server issues tokens back to the client. So this is relatively simple. And then next slide, please. And then the redemption side, we have 4 different running modes. So essentially, the first is single verifier, and this is essentially the simplest running mode in the sense that it maps almost identically to what we present in the PrivacyPass protocol document. So clients essentially just redeem tokens directly with the issuing server, like the same fully qualified domain name, and the server just returns the response or performs some other action based on whether the redemption is successful or not. Next slide, please. So the second mode is delegated verifier. In this mode, an intermediate verifier asks for a PrivacyPass redemption on behalf of an issuing server, and the client sends the redemption token directly to the delegated verifier, who then forwards the redemption token and to the issuing server and gets the redemption response back from that issuing server, and then performs some other action and can propagate the result back to the client. So in this scenario, there's obviously the concern that the intermediate verifier could just steal the client's tokens, because the client's essentially just stealing tokens. And so I think here there are some extra mitigations that we should probably put in place on this initial redemption between the client and the intermediate verifier. And I think in the HTTP presentation after this one, there are options for doing that. So next slide. The third mode corresponds to an asynchronous verifier. So in this mode, the intermediate verifier asks for a redemption, but instead of the client sending the redemption token directly to this verifier, it performs the redemption with the issuing server. And the issuing server creates this signed redemption record, which it either forwards to the verifier or it returns to the client. And these signed redemption records are covered in the HTTP API document, and essentially they're signed under some server signing key, and essentially attest to the fact that the client has performed some valid redemption in the past. And the client can then use that signed redemption record with the verifier to prove that it has a valid redemption. And there's some caching things that we can do here. And again, this is a running mode that's used in the HTTP API documents. I think Stephen will be talking about that in more detail. Next slide, please. And so the final mode relates to public verifiability. So in the previous 3 running modes, we assume essentially a symmetric exchange whereby the issuing server is essentially terminating all redemptions in the end. And in the public verifier mode, we assume a different property on redemption tokens in that they are publicly verifiable using the server's public key associated with the protocol. So any verifier in the ecosystem can ask for a redemption token for a given issuer and verify it based on the server's public key. And what's important to note here is that we don't support this in the current core protocol functionality, but as Armando laid out, there are potential ways of coming up with different constructions of the PrivacyPass protocol that satisfy this property. And so this is something we want to allow in the architecture framework as well. Next slide, please. And finally, the fifth question that I wanted to talk about was the privacy analysis. How do we actually quantify the privacy of a client in the ecosystem? So some of the important factors to consider. So the total number of servers in the ecosystem corresponds directly to the number of keys in the ecosystem. So a client holding tokens for some set of servers essentially binds itself to the anonymity set of all clients that also hold the same tokens. Because if we assume there's a malicious verifier in there that can trigger redemptions for all for all issuers, then this verifier can check what tokens a client holds. And so if we increase the number of servers and the number of keys in the ecosystem that clients can have tokens associated with, then we see an exponential decline in the size of the anonymity set that the client belongs to. A related point with any privacy-preserving technology is that the total number of clients in the system obviously gives an upper bound on the anonymity set size of all the clients, because you just belong to all the clients in the ecosystem. But likewise, for the number of clients accepting tokens from a server, you bind yourself to that anonymity set. So if you're part of only a small group of clients that accept tokens for one particular server, then anyone triggering redemptions that you reveal for that server, you bind yourself to that small group. So this is obviously an important factor. And then at a more granular level, some of the extensions we've been talking about may add small number of metadata bits inserted in tokens. And essentially what these extensions do is use more keys on the server side for issuing tokens while still maintaining the PrivacyPass API. So obviously, by introducing more keys, you essentially introduce more servers. And so the privacy loss is very similar. And so we want to limit the additional metadata bits as much as we can. But obviously, there are functional reasons why metadata is useful in the protocol. So there's some sort of trade-off there. And then the final 2 points relate more to how a malicious server might act in the ecosystem. So a server's key rotation cycles, as I mentioned before, correspond directly to if a server's performing lots of key rotations, then you will have tokens in smaller epochs, and so you'll be part of a smaller anonymity set. And likewise, the reason we assume independence of key registries is because potential collusions between servers and key registries could lead to servers posting different keys in different places, which would then potentially tag clients into, again, smaller segmented client bases. So next slide, please. So one of the things we do in the document is try and concretely parameterize what we want the ecosystem to look like. And so this table is taken from the document. A few of the things I wanted to highlight currently is that we have firstly is we have these fixed values, and it'd be good to get more opinions on what is actually same value for a minimum anonymity set size, what recommended key lifetimes of applications do they need? Can we afford to have smaller key windows? I guess this is all. These things are all related into this final equation, which is in the third like sort of box here, and that's one of the biggest restrictions that we currently have in the document, is that the maximum allowed servers is logarithmically like related to the like total user base essentially. So the reason for this is obviously related to the fact that the number of servers, introducing more and more servers sees an exponential decline in the anonymity set size. And so we have like some fixed values in the document where we say like if there's like 5 million users, and I think we can like permit like 5 or 6 issuing servers, which is obviously like a really restrictive clause on the ecosystem. And so this is something we want to think more about. And next slide, please. And one of the mitigations that we actually present at the moment is that rather than having this like hard restriction on the number of servers, we can think about instead having the maximum number of client-supported servers at any given time. And what this means is that like if a client supports, if a client holds like tokens for 4 issuers at a given time, then if a client was to try and try and be issued tokens from a new server, it would have to delete tokens from one of the existing servers that it holds. And so what we're trying to do here is like simulate an ecosystem where a client can only hold tokens for a small number of issuers. And if we can do this effectively, then we can remove the restriction on the number of issuers, because we could have a large number of issuers, but clients only supporting at any given time a small number of them. And so this limits the sort of possibilities for segmenting the client user base. Although I should note that this logarithmic equation we have on the right doesn't necessarily directly translate to this setting, because a client can hold tokens for 4 issuers and client B can hold tokens for 4 completely different issuers. So there is some privacy disparity in these 2 different things. But I think going down this sort of angle might might give us some alleviation on this restriction. But it would also be good to hear more opinions on whether there are different mechanisms for like avoiding this like total bound on the number of issuers. So next slide, please. Finally, the extension policy. So Armando laid out what we currently have for the extension policy. I know there's been some discussion on this, but essentially what we currently have in mind is like any extension to the protocol is essentially just going to introduce new cypher-suite identifiers, and those cypher-suite identifiers will have to be supported by the key management framework. And likewise, any extension, if it introduces new functionality like public verifiability or additional metadata, is going to have to update the privacy analysis, because using these new cipher suites is going to lead to slightly different privacy analyses for these extensions. And so that's something that any extension to this protocol would have to bear in mind. So next slide, please. So I think just to wrap up now, in summary, like the architecture doc like analyzes the PrivacyPass ecosystem as a whole and focuses on like the interactions between the clients and the servers and all the different parties that are involved, well, they're a part of this ecosystem, and how like clients and servers retrieve data. And one of the core guiding like principles of the document is to like ensure that everything is being done in such a way that we can like parameterize the privacy of any given ecosystem in such a way that we can predict what sort of like anonymity set sizes we can expect, because it's only in this context where the protocol actually has utility. And so that's what we're trying to do with the architecture document as a whole. And then finally, in the next slide, just to like raise the open questions that I brought up throughout this presentation. So we have 3 core open questions, but there's a lot of room for discussion on a lot of different topics. So the 3 core ones that I at least picked out were getting suggestions for mitigating against server centralisation, and whether we do that in this document or whether it lives in a more like specific document related to, well, within the working group. The second question is around the key registry. So we give guidelines and we give assumptions based on what we think the key registry should do, but should we be specifying this more concretely? And if we should we do it in this document, or should it be done in a different working group document, or should we be borrowing technology from a different place? And finally, around the topic of malicious servers, like how should we be identifying these servers? This also relates to key registries, and when we do this identification, how do we then react to it as an ecosystem? So that's everything from me. Thank you for listening, and happy to take questions.
Ben Schwartz. I would encourage people to jump in. We have some time here to discuss, especially if you have suggestions on how the working group ought to go about addressing these issues. We aren't going to solve them in 10 minutes here. I just wanted to clarify, this doc says a few things about server centralization and malicious servers. Should some of those say issuer?
Yeah, so servers and issuers are kind of, like, I'm thinking of them identical, but essentially I wanted to like differentiate between like these intermediate verifiers that can like ask for client redemptions, but essentially by server we're talking about like an issuing entity that issues tokens to clients.
Mark, we don't hear you.
Let's see. How do I do this? Let's see here.
We hear you now.
Okay, great, thanks. So a point on this first bullet, this is in the charter addressing this issue, this centralization issue. I have two sort of responses here. My feeling here is that this would be a separate document. It's not really an architectural, I don't think that it's a traditional architectural issue. It's also not an obvious protocol issue. But I would also want to tie these together. Let me see if I can make sense of that. That as the architecture and protocol documents go forward, I'd like to see this centralization document also move forward so that they are sort of tied together, as it were. And for the chair's information, this is something I'd be willing to volunteer to work on. But I just don't see this issue as being something that you would address in a traditional architecture document. I could be convinced otherwise. And your slide number 7 sort of gets at the issue. You don't have to go back to the slide, but it was in your presentation. And so, in reacting to this first bullet here, I guess my 2 points are that I really do see this as a separate document, but I'd like to see them tied together so that the architecture and the centralization paper or the centralization draft move together through the approval process. Thanks.
Thank you, Mark. Stephen, you're up.
So I guess one question is, like, a lot of these, like how we deal with server centralization, how we do key registries is going to be somewhat use case dependent. And I guess like how much we want privacy pass, like the architecture or centralization doc or whatever, to like limit what the use cases will do versus like providing a like guideline for like what things should be taken into account here. I think given that, like, yeah, I think maybe making this separate from the core architecture doc makes sense. But I guess there's also going to be cases where like a key registry just is like a lot of overhead when your like use case doesn't really need that. And I guess seeing like to what extent the Privacy Pass working group documents want to support different use cases built on top of Privacy Pass is another question.
Yeah, I think that's something that we're currently aiming for with the architecture document, is kind of like giving these like more like high level guidelines on what things should look like, and then hopefully like the use cases will like take on those guidelines and give like more concrete constructions of the like particular different like entities that are involved.
Oh, my apologies. Richard. I'm sorry, Richard and Robin. Could you, Richard? You're popping in and out. Okay. Robin, you're up. I see you. I don't hear you yet. I hear you now.
How's that? Okay. Yeah, so thanks for this, and thank you for setting out the explanation of the entities. Having lived through a few other kind of federated architecture discussions, I think you'll need to have a clear conceptual model that tells people new to this exactly what the difference is between things like a credential, a token minting server and a token redemption server. And it sounds to me like there may be a couple of other roles that have emerged from the discussion. For instance, the token minting server for a given attribute might not actually be the authoritative source for that attribute. So, for instance, if you wanted to assert the fact that you have an HGV license to drive a truck, you might go somewhere to get a token minted to that effect, but the place you went to might not be the vehicle licensing authority. So that kind of distinction comes out of the use cases, but I think it's really important to reflect in the conceptual architecture. Otherwise, folks get confused about server.
Yeah, I think you're right. I think there's we're not quite clear on exactly what like an attribute corresponds to in the ecosystem right now, but the way we're thinking about it is like a given server that issues tokens is issuing for like one attribute, and that's what the like bit that you get in your token is like corresponding to. So in your example with like a driver's license, there would be like an issuing entity in the ecosystem that issued tokens for that thing. And there was a key, there was like a specific server key that did that. So that's the model we're looking at. But yeah, I think the document could definitely incorporate that sort of relationship.
Thank you, Robin. Richard, you are on the air.
All right,
Although I don't
audible?
see you. We do
Am
hear
I
you.
audible now? I'll go audio only because who knows about getting video working. So I'm relaying a point. I got out of band from Chelsea Conlow of Waterloo University. She's on the MP3 stream and not on text chat. She points out that in the case of Tor, if you have an anonymity network like Tor, then you can detect malicious key registries by doing something as simple as building multiple circuits to a key registry and doing parallel key registries and comparing the results. So there may be some mitigations available if you assume some extra technologies. She also observes that if you don't have an anonymity network like Tor, then you have identifiers like IP addresses that can be used to do external correlations. So there's a limit on how much you can get from these sorts of things anyway. So there's a couple of points from Chelsea. I would add on top of that as well that it would be interesting to me if we could see if there's maybe a couple of additional assumptions one could make that you might get from the environment anyway, kind of like the IP address tracking stuff. Anyways, that could perhaps simplify the number of mechanisms we have to employ here. Because this is looking kind of on the edge of, the IETF is not all that good at doing hard things. It's looking on the edge of the hardness that is plausible to achieve in the IETF.
Yeah, I think they're good points. I think the point about it's important to emphasize that the PrivacyPass protocol only provides anonymity to the extent in which it is then used in like a broader framework. So yeah, it's true that if you have other identifying features, then they will reveal who you are. And I think on the Tor thing, it is interesting, and I guess I wonder whether like using like technologies like that, would they belong to like an external auditing process, or is it that when clients go and retrieve key information directly, they do it via like the Tor network, for example, or a different technology?
If I were to try and kind of knit those two comments together, I think one of the ways you could adapt the approach here is if you're willing to say, in certain circumstances, you can detect malfeasance by doing sufficiently diverse requests. Maybe you don't need to build a bunch of malfeasance detection into the base protocol, right? So it's kind of one of those assumptions you might build in, or you could do as opposed to you have to do all the time to simplify down the base case.
Mm-hmm. Yeah, I think that's definitely an avenue that's worth pursuing. I think that kind of like fits into like how we currently think about the architecture document as a whole as well. It's like providing these like broader guidelines.
Yeah, thanks.
Okay, thank you, Richard. I think we should move on to the next presentation.
Hey, I'm going to talk about the HTTP API draft that we currently have as a potential item for adoption next draft or next page. Similar to the other presentations, this one builds up on top of the core protocol and some of the concepts inside the architecture draft. Next slide. The general layout of the draft as is we talk about how you would wrap a lot of the protocol messages throughout the inside like an HTTP header and well-knowns, talk about a bit of how the key management would work in a HTTP setting, and then talk specifically about the issuance and redemption protocol and messages that are being sent back and forth. Next slide. So for the initial wrapping, we use a new sec privacy pass header that is attached to these well-known requests. The reason to put it in a header instead of throughout the body is that there's a possible idea of like moving this off of just being well-known endpoints and like letting an issuer do privacy pass issuance and redemption at any endpoint. For example, for a CAPTCHA server, you might want to have the endpoint that receives a CAPTCHA result be the one that's also giving you back your privacy pass tokens. Redemption, you may also want to also return other information other than just the like, yes, this token was valid, or no, this token wasn't valid. In order to actually package all this up in this header, we are looking at using the structured header, which is a HTTP BIS draft currently in that working group, to encode the type of message that is being sent, whether it's an issuance or a redemption request, and the actual protocol data inside of it. Next slide. So for issuance, the privacy pass header, for the most part, contains all the blinded nonces that the client of the issuance would want to send, probably stacked up and batched together, since you don't want to do one HTTP request for each token. I think depending on the underlying schemes, we'll need different batching situations. That way you don't have one zero knowledge proof for each and every token. And there are some schemes in VOPRF that allow for batching. The response would then contain these signed blinded tokens in the same header with a separate message tag. And the server would be, or issuer would be responsible for using the other data inside that request to determine whether to send a token back. Either if it's a CAPTCHA challenge, verifying that challenge, if you have some sort of authentication or login information, using that to look up your isHuman attribute, or whatever other policy the server might use to determine when to issue tokens. The client would then be responsible for storing all this under some sort of storage that is specific to that issuer. Next slide. For redemption, the process gets a little bit more complicated depending on what form of redemption you want to do, as described in the architecture doc. The generic way of doing redemption is somehow you've gotten the issuer's configuration, be it from a key registry or some other side channel. You verify that before you send a token, since if it is out of date and the client doesn't want to support old tokens, since that might involve additional anonymity sets, you don't want to be sending your token at all. If all that information is valid, you do a new request using the privacy pass header. Again, this by default is currently to the well-known address, but could reasonably be extended to just be any endpoint on the issuer server. The server does the whole verification step and then returns, for now, a signature that says, yes, this token is valid. This signature is not too required when the client, which is redeeming the token, is immediately consuming the result, since this redemption was hopefully done over some secure channel, HTTPS. But is more useful for the other forms of redemption. Next slide. So this is just the direct, like the client that is talking to the server is the one who wants the result of this privacy pass token. And this is the single verifier and delegated verifier redemption running modes from the architecture document. One part that, at least in the HTTP API, is we have the client also send some sort of target so that we know for a fact that the person returning the redemption result is returning it for this particular redemption request and isn't like just replaying some old redemption request. This is mostly only useful if like you're worried about a malicious issuer or verifier that is trying to do something funny, but this is more useful in the delegated case. Next slide. In this case, the person asking for a verification of a token isn't actually the person who's going to be consuming this in the end. So instead of putting some arbitrary data in your target, you put something that binds this redemption to like the current instance that you're redeeming for, be it like the top level site that you're redeeming for and the current timestamp, or who you're going to eventually pass this redemption result to. You then do a normal redemption and you get that response. And now this response you can pass along to whoever you were actually intending to delegate this redemption for. And since it's signed by the issuer and contains this context-specific data, the delegated party can verify that this redemption is correct. This is useful both in the case that the final party doesn't actually want to be doing a redemption for every single token they receive, since they may be receiving large amounts of QPS while the client is only going to be doing one redemption in this instance. It's also useful if in the web case where you have a lot of parties you want to pass on this proof to, but you don't want to be using one token for every party, though that's more limited based on the use case that you're using this API in. Possibly like in the web HTTP use case, this would be useful for a lot of third-party content embedded on a top-level site, and each third-party content doesn't care about getting like a unique token. But I think it's an open question to what to amount to support this sort of redemption in the protocol. Next slide. Next slide. So for key management in this API, it's very similar to the descriptions in the architecture doc. We need to worry about anonymity sets based on the keys used. Notably, we are also worried about like if the keys change over time, we don't want to like have some clients under old keys and some clients under new keys. So we need both like some enforced standard rotation limits. Otherwise, like an issuer can just change their keys every 5 seconds and have a bunch of keys in play. So we need this sort of consistent keys across the ecosystem. But we also want some form of audibility so we can detect when an issuer is acting badly and changing their keys very frequently. There's a number of ways you can then optimize on top of this, assuming you have this append-only consistent log, which it's a question whether the working group should be defining it this sort of log or leaving it to the use cases or something else. I think the term key transparency and cert transparency has been thrown around as possible ways of doing some sort of log. Next slide. One optimization, assuming you have this magical log, is if the client doesn't want to be talking to the log for every issuer, it could just talk directly to the issuer itself, though it would need to do this in a anonymous way that doesn't have any information that the issuer could use to figure out what user you are. The issuer would then return the key commitments, and if it had some sort of inclusion proof or something to verify the authenticity of the key commitment and to prove that it's been submitted to a log, that may be sufficient for the client to trust that. It would reduce QPS on the key registry and allow us to not have to have a key registry ecosystem that is capable of receiving requests from every single client that wants to be using this ecosystem, but it does have these additional issues of you have to worry about old key commitments being presented by the issuer if you don't have some sort of small time span for the inclusion proof, and also having to spin up some sort of inclusion proof gossip protocol for the key commitment registry. Next slide. So some other alternatives that may be reasonable for getting these key commitments is doing just the request directly to the key registry at a well-known. This is probably the simplest and most straightforward, but possibly doesn't scale well. Also, depending on the clients that are using this API, they could have centralized proxies to, like, if a UA fetches all the key commitments globally for all users and then presents those, that proxy, if it's oblivious to who the client is in any state could serve as a intermediate to prevent a ton of traffic from hitting this key registry. Next slide. So yeah, some of the open questions left from the current draft of the HTTP API is whether we keep this concept of protocol endpoints using .well-knowns. Currently, we have a well-known for issuance, redemption, and the actually getting key commitments, or whether we generalize this so that the issuer can use any endpoint to do issuance and redemption. We need a concept of like how you would do double spend protection for the issuer side at scale. It's fine if the issuer is just a single server, but like in many web scenarios, your server is actually a bunch of different servers among a lot of different data centers, which may have different amounts of eventual consistency. And discussing whether global eventual consistency, what properties globally having double spend protection versus per data center, and like what the privacy trade-offs there may or may not be a thing worth including either in this draft or another draft. Discussions about the actual policies we want for allowing key rotation and for these key registries to enforce, and what sorts of key management strategies we actually want to include in this draft versus leaving it up to individual use cases or generalizing it into an architecture draft or other draft. There's also a question of, this is mostly a low-level HTTP API for how to interact with privacy pass as a core, but we'll also need some sort of higher-level APIs, probably in other standards groups like the W3C, for actually having like browsers communicate with issuers, and to what extent we want to maintain consistency with those or just leave that up for other groups to have to be consistent with what Privacy Pass puts out. I think that's all.
Okay, please bring your questions to the mic. We have 30 minutes remaining in the session, so if there's any discussion that you want to open up here, it's you know, we're not pressed for time. While people are thinking, I would also like to remind people that the authors have requested adoption for each of these drafts, these 3 drafts. We're going to be following up with an adoption call on the list for each of these drafts. So please remember to go read through the drafts and ask any more follow-up questions that you have so that everybody can make informed comments on adoption.
Hi, yeah, Alex speaking. So I guess from like our perspective, like one of the things that we'd like to like raise is the key management story, and I think because we have a good idea of like what we need from these things, and we like talk about it in different documents, but it would be good to get like more opinions on what would be like a satisfiable solution to the problem, like from like an auditing perspective and also from like a functional perspective. So if there was some discussion on that topic, then that would be useful for us.
Hey, I'm kind of a tourist here, so I don't know this particularly well. I'm wondering what the intended use cases of this are. What kind of data you would imagine would be transported across these?
I guess from the BOF, we actually wanted to like generalize some of the use cases, but some of the like base use cases we've been considering is things like if is a human bit, for example, capture results. If a website has a strong reason to believe that a user is actually real, and being able to pass that on to other websites that may not actually have the capability of gaining that information.
How do you stop someone clicking a capture once and then doing a million operations that require capture? So that the whole point of a capture is that it's a proof of work as well as a proof of identity.
So if you complete a capture, we imagine that the issuer would then return some number of tokens, and then eventually those tokens would be used up, so the user would have to come back and do another proof of work to get more tokens. It would be up to issuer policy to see how many tokens they would give out for a certain amount of proof of work. So currently, even some capture systems do work in this way, that once you've completed a challenge, you have a set amount of trust that gets expended as you visit a lot of different sites and use that up.
And just to clarify, tokens are intended to be single-use tokens, so that's how you.
Yeah.
Yes.
But if you get a million tokens minted by one person that you've paid to go click on buttons in order to allow your spamming operation to run, then obviously the spamming operation can do a lot more damage if it gets a lot more tokens. So the privacy part of this and the fact that it can be used across many sites then allows that minted token to be used with a lot less ability to track it back to where it came from. So I'm not sure that you don't open up a giant abuse hole here, and I haven't seen how that abuse hole doesn't exist for that case. So I was wondering if you had another use case where this has value.
I mean, even for that case, if the issuer is setting limits on how many tokens a specific user can receive, then that somewhat limits it, and it's still required. If they trust their proof of work is enough to be equivalent to a user interacting with sites, then we have similar issues in the current world where if you have a bot farm in one place that is just a lot of people clicking through captchas and getting lots of tokens, I guess, effectively. Really, it's, I guess, in third-party state at the moment. They could do actions like that. Yeah, I guess there is the disadvantage of since tokens can't be tracked back to where they were issued, you'd have to have either tighter bounds or harder rate limits on how often tokens can get issued to a particular set of proof of works.
Certainly, if you are increasing the value of one of these things once it's created, then that the trade-off there is that it can be used to do more damage, and hence the attackers can spend more on getting one of these than they can on clicking on a capture.
Yeah. I think it would require a decent amount of infrastructure to avoid your captcha just turning it into using privacy pass and not becoming a huge threat vector, but I think there are some rate limits that will help with that. I guess alternative things are if you have more of a user identity and that user's use of your website has made it so you believe they're human, then you can associate how much trust you've given them, how many tokens you've issued to whatever identity you have in that case. So I guess you'd need to be a malicious actor who registers a bunch of different accounts and gets a lot of tokens in such a way that you're not detected. But I think
the not detected is what I'm wondering about here, because the whole way that an abuse loop works is that if you say this user is valid and they behave badly, then to close that loop back, you get a report that that particular user behaved badly, and you can then associate that back to who you've been handing these tokens out to. So if you have a badly behaving user that you're giving tokens to, and they then go out and use that decreases the trustworthiness of you as a token issuer, and you don't know where the leak is.
I guess to some extent it's also people who then consume these tokens will have to if they see a lot of bad actors from certain token issuers, and their value of that token issuer will decrease. But yeah, I guess there's not the immediate
the token issuer can't see where their problem is. That's the problem. As soon as the token issuer has more than a handful of users, they can't tell where the abuse is happening.
Yeah.
Which appears to be by design. So yeah, I can imagine that this thing wouldn't have value to anyone who needs to protect something because it has that abuse hole in it. So I'm not sure what value it adds. Basically, I'm not sure of the use cases that are not trivially bypassable by a bad actor.
Yes, to some extent.
Sorry. So I think our perspective on it is like like you're right in that turning like some sort of proof of work into like a finite number of tokens obviously allows you to then enlarge in any like malicious actor's ability to like to do that as well. But I think the key idea here is like these tokens are privacy preserving, and they act almost as like a cross-domain cookie in a sense, because you can like get them from somewhere and use them in some other place if, like, say a server is like running different domains, and you still maintain the privacy property. And I think the concerns that you're raising as well sort of are prominent in a lot of privacy preserving technology, and that's a trade-off that we're aware of, but we're on the like privacy side of that trade-off right now, because the use cases that we have that we want to ensure that clients using these tokens in different places are remaining private. And in terms of the mitigations, it's more of a case of like you rate limit and you do double spending, you do double spend protection. And if you're under attack or you have some resource which is like really you don't want people to access using these tokens, then you just don't accept them.
Yeah, I mean, I work in the email spam world, so I see a lot of the cases in which malicious actors occur, and designing a protocol that, as someone said in chat, fails under malicious actors or fails under load, that's tricky because it makes it reasonably easy to take something offline.
Sure, that I mean, yes. But I guess you don't have to accept the tokens. We're not like, and I think this comes into like the centralization question as well. I think these are all good points, because if you centralize things and say like there's like, for example, like if you control different websites and you accept tokens on people's behalf, then yeah, you have a good point. I think by building like a diverse ecosystem of providers and also verifiers that accept these tokens and provide like guidelines under which you accept them in safe circumstances, then they are the scenarios we're aiming for right now.
All right, well, I look forward to seeing how it plays out. I guess if you don't have to accept the tokens, and if the clients can't depend on you accepting the tokens, then that's a different story. Cool.
So I have a kind of unrelated question. To do the key management or key registry or whatever, does that mean there's going to need to be a secondary organization similar to the CAB forum, which has and baseline requirements for issuers? Will there need to be this whole other ecosystem of infrastructure?
I think to some extent this is dependent on like the use, like where these privacy pass tokens are being used and the like ecosystem that is built up around each particular use case. I imagine like if this is just a web-based like fetch JavaScript API, like the person making these policies would be some sort of either individual UAs browsers or a like group of browsers who have come up with a centralized policy. So similar to the CAB forum, though hopefully we're not going to have hundreds of thousands of issuers, and you can scope these policies in such a way that some amount of this is technically verifiable if we have some sort of like append-only log that you can verify these key rotation periods. But yeah, I think to some extent each ecosystem is going to need to come up with some sort of base guidelines. I don't think we can come up with a like complete architecture for all valid for all ecosystems.
I put myself into the queue, chair hat off, just to say on the topic of abuse, while the privacy preservation does make certain kinds of abuse defenses harder. I think I have 2 points of optimism to share here. One of them is if this is used in a proof of work scheme, then the issuer can set the amount of work per token high enough that the spam, essentially that there's no spam profit margin, that there's no net benefit to a spammer from harvesting these tokens. And conversely, the redeemer can control the amount of, for example, the number of page loads, essentially the amount of benefit that it provides per token. And so it can also essentially reduce the benefit per token until there's no net gain from token harvesting. That's one sort of angle of this. The other angle is there are closed universe use cases for this, where there are a finite number of potential token holders, and each of them is rate limited independently. So as long as tokens are being issued subject to some finite global rate limit on a reasonably fair basis, and the redeemers have some finite capacity limit that they're capable of producing, like the total number of QPS they can serve, then they can simply make sure that in the event that all of the tokens were being redeemed at the rate limit, that they would still come in under their capacity. So those are just some reasons why I think there's a chance this all might work. On the air.
Am I sending?
Yes, we hear you.
Excellent. So, question. I'm seeing we have these multiple verifiers, right? That can verify these tokens, but we want to make sure that the token isn't redeemed multiple times. So these verifiers are going to have to coordinate in some way to make sure the tokens aren't double redeemed. I guess I'm not understanding the scheme by which we both verify that the tokens aren't double redeemed and also don't create a single point of failure that can prevent token redemption.
Alex, would you like to respond?
Yeah. Hi. Yeah, you raised a good point, and I think the situation we're assuming, at least in the architecture of HTTP API, is that you have that each verifier has its own eventually consistent double spend protection, and and that double spend protection only corresponds to that verifier. So there's no like global double spend check for all the verifiers in the ecosystem. It's concentrated to a single verifier. So like the caveat then is that a token can be spent once with every issuer. Once with every verifier that's accepting tokens for a given issuer, and yeah.
Okay, so the double spend is kind of a weak protection.
Yeah, exactly. One of the reasons why we don't enforce double spending, we kind of give like recommendations, is because, I mean, firstly, there are some situations where people have brought up in the past there might be applications where double spending might be okay, though you do lose like the linkability property when you do that. And secondly, because with the restriction in mind on verifiers acting independently, that there's not really a good way of doing global double spend protection. So it's really something that you'd want to implement as a verifier in order to like prevent people attacking your systems by spending multiple tokens.
Okay, and second, the double spend protection is going to require remembering all of the unexpired tokens that have been spent. So do we have a way to make sure that verification systems don't wind up effectively being attacked by systems creating and spending tokens to fill up those buffers?
Yeah, so tokens are only valid for the key pair that they're issued by. So when a server rotates its key, it should also clear out its entire storage. So one of the trade-offs with like the key cycles is we don't want them to be too small, but we also don't want them to be too long for the reason you bring up, in that clients could just like fill like a server's like token storage system for checking double spends. So the key rotation should also be short enough that the server is able to like store things efficiently and check things efficiently. But the idea is that then they can just get rid of everything. They can get rid of their entire state essentially when they rotate their key out.
Interesting. Thank you.
And also like with these token storage systems, like you can use like efficient data storage mechanisms as well, like bloom filters and things to mitigate against like the size of that storage increasing. So you only really need to check that things are contained, that you've seen things in the past. You don't need to keep like the entire list of tokens.
Okay, we still have a couple minutes left if there are any more questions, but I think we may be winding down. Okay, well, I think we're probably reached the end of the conversation for today. I think next steps are to, hopefully have more folks read through the documents so we can continue discussion on the list. And, in a short period of time, we'd like to, as Ben mentioned, call for adoption of these documents and see how the group's feeling is towards that.
So thank you to our note takers, and we'll see you on the list.
Yeah, and hopefully maybe we'll see some people in person sometime. But thank you for all attending.